Hi everyone, today I'm going to show you how to calibrate a model. Basically this is a HEC-HMS model. If you want to calibrate your model, then you can follow all these steps, and in my previous videos I have already demonstrated how to set up the model. So this model is pretty small, not that big, but if you can develop a model that is big, it doesn't matter. But here you can see I have only 9 sub-watershed here, sub-basin 1 to sub-basin 9, and I have only one outlet for this entire model. I didn't even add more because I have only observation data at the outlet of this watershed here. So if I want to turn on the DEM, you can see from view map layer, and I can turn on the terrain, and you can see it's there. So that is my model. The area is not that even steep, it is kind of flat area. Now located somewhere in Illinois. Okay, so here I'll even calibrate the model for all these sub-basins and the reaches I have. I have only 4 reaches, the rivers that are even connecting these 3 sub-basins locating upstream of this watershed. So let me explore what I have here. In my sub-basin, if I want to show you what method I used, so I'm going to show you from parameter. I use this canopy method, a simple canopy, right? I have used this ones. And then for surface method, I've used simple surface. And for loss method, I use SCS curve number. You can see that is the curve number, and for initial abstraction I estimated these values 0.5, and the curve number I have is 0.80, and it's 85, and impervious percentage of imperviousness is 20%. For transform method, I used Clark unit hydrograph, and you can see we need to estimate all these parameters, time of concentration and a storage coefficient. So I have these initial values, and then I have the base flow. So for this case I use like constant monthly. For each of this month I have these values for each of these sub-basins. And then for a routing method, I use Muskingum. And for Muskingum, you know that, okay, we have 2 parameters like Muskingum K, that is the travel time we need. And we have another X value that varies from 0 to 0.5. So this is my first estimation of the model parameter. And if I run the model, you can see I have already generated the run. And here you can see the run. Okay, before going to run the model, I can even show you other parameter I have. For mat model, I use like specified hydrograph, and for time series, I have precipitation time series. I used only one single gauge for the entire watershed and the study area. So that is another challenging task to calibrate the model, and you can see that this is my graph, the rainfall data I have here, the hydrograph. I have rainfall depth in inch, and I have this kind of shape. Basically, this is an event-based model. And for observation, I have the discharge, and you can see the plot is like that. So we have pretty flat top of the hydrograph, and if you run the model, you'll see here, because the model is running for a few days, it's not that even slow, and I can see the results here. So we have the global summary here, we have the summary, and then we can see that the outlet, because we don't have anything for other sub-basins, so we can see the plot. So you can see this farm line. This line is basically the accumulation of all of this watershed, right? All the flows coming from the upstream watershed and sub-basins. And then that is the black line. This is the observation. So our goal for today is to match this line, this blue line, to that black line, right? So that is pretty challenging because the observation we have, it has a flat top. It should be like that, but because of some storage of water or some intervention with a dam right within the study area, I already checked it, so the curve is like this. So okay, we'll try our best to capture that observation using our model, whatever parameter we have. So let's see the summary table. The present condition we have, like the NAC value is 0.26 and the percentage bias is more than 30%, right? And the RMSE we have like 0.9 standard deviation, and the peak discharge is like this, but from observation we have computed is this, and this is the observation. So our model is basically underestimating whatever observation we have. So let's see if we can even capture the shape of the hydrograph using our model. So for capturing that one, okay, I can try, because I don't know how to even approach the process, but from my experience, what I do, I start with the loss, because this loss factor is very important, because our model is generating a hydrograph that is even lower than the observation. That means our loss is higher than the actual loss, so we have to reduce the losses, right? So we can do it, because see, if we don't know, because we have 9 subwatershed, we have even 4 rivers or reaches, so how can we even approach the calibration? It will take a lot of time. So at first we'll try with automatic calibration, and then we'll try to fix it using a manual calibration process as well. So for automatic calibration process, what I can do, I can even add that compute, or from compute you can go to optimization trial manager and you can go to new and optimization 1. I'm using my basin model. I have 3 basin models, so basin model is there. Clicking next, I have 1 met model and everything is same. So I think it's there. It's there. So it doesn't have any parameter now. So what we have to do, we have to even go to search and use the method, right? Simplex method. We can use the simplex method, and then for maximum iteration I can even select 100, and the tolerance I can select 0.01. And for objective function, you can see we have these options: root mean square error. And in order to capture, you can even use first lag autocorrelation. You can use peak weighted RMSE if you want to capture the peak only, if you are not even bothered about other base flow and everything. Even if you want to capture the volume, you can use this one, but for my case I'm using this root mean square error. My objective function will minimize this RMSE value, and the location I have, it's the outlet at the downstream of the entire study area. And for start time, end time, right, we know the like time is 0, 0, 0, we know this, and I'll show you the date as well. So here, what is the date? We can even get it from our control specification, right? It is from 18 to 24. Okay, 18 to 24. I'm just pasting it there. It should be 24, 18 to 24, 0, 0, and then it has to be like 0, 0. Okay, we have this. So the time interval is 1 hour. Okay, we can keep it 1 hour, or we can keep it 15 minutes. Usually I do it for 15 minutes, right? So we have this, and everything is there. So for this one, we can even use the same thing again. It should be 0, 0, and then 0, 0 hour. Ending time should be the same, but this should be 24. Okay, ending time. So that's it. Even now we need to add our model parameters. So add the parameter whatever parameter you want, you can add, because we have subbasins and we have 4 reach. So for each of these reaches we have like 2 different mass income parameter X and K. So we need to add like 8 parameter for those 4. And then for subbasins, we can use all subbasins, and we can even check it. Okay, for first parameter, we can use all subbasins, and let's see what parameter we have. So we're not gonna calibrate simple canopy, simple surface, because these are the parameter value we already estimated from literature. We don't need to calibrate those because it has certain limit, so we can't exceed that one. So we can even calculate curve number, but this is calibration parameter, initial abstraction scale factor. I can select that. And for parameter 2, when you can check the initial value, they're giving like 1 and the minimum value is this, but for our case the initial value is 0.5, right? We already checked that. And the maximum value will be 100. These are basically in inch. Okay, so this is the factor. So since it is a factor, we have to use 1, no problem. And then for parameter 2, we can select all subbasins, and then here the parameter will be the next one, SCS curve number scale factor. So initial factor is 1, maximum is this, minimum is this. And now we need to add the mass income. Okay, so we have 3, we have to add more, 5, like 1, 2, 3, 4, and 5. So starting from 3, I can select river 1, and for river 1 mass income X, and for so the minimum HR, it should be like 0.1, otherwise the model won't run. The initial value we have, it is this. And then we have like parameter 4, we can select river 4, and then X, the minimum value is 42, and maximum is this. Okay, minimum will work. And for this one, select river 3, do the same thing again, K, but for K, just reduce or increase the time, minimum time to 0.1. And for 3, we have to add another parameter X, and I can keep it as it is. For river 2, we have 2 there, select K, keep this value as 0.1, and for parameter 8, we can select river 2, and this time we'll select X. And for parameter 9, we can select river 1, and this will be X, and increase that to 0.1. And finally, we have to select again river 1, and that is the X. So we are done with our optimization. We can save the model, right? You can see the graph, you can remember that. So the current graph we have, that is the graph. Even we can see it pretty clearly that okay, we can delete extra curve we have here. So that's that. So that's the difference between this observation and the simulation. Okay, you can keep that in mind, or even I can even keep it. Okay, and now what we have to do, we don't have any trial run right now, right? So what we have to do, we have to select that and hit it. Then it started the optimization process, and it will take a while because we specified our maximum number of iteration is 100, and we added all these calibration parameters from basins, right? So we are using initial abstraction as our calibration parameter because we don't know how much water will be abstracted at the very beginning of the rainfall, and we are using the curve number, right? So we calculated the curve number from land use and land cover information, but this is basically a calibration parameter we are getting from the model. So we have to fix that. Let's see if we can fix it. So what is basically we're trying to do here, we're trying to match the observation with the calibration. With the observation with the model generated hydrograph. But if you see, right, previously you saw the peak is pretty flat. So it's even challenging because we know the typical shape of a hydrograph is basically a flat hydrograph. I'm talking about the flat hydrograph. So we have the rising limb, we have a recession limb, and we have the peak, right? But for this case, the peak is pretty flat, so it's pretty challenging to capture. So we have to even try, and if you can use manual and automatic calibration that is currently going on, we can even capture it. So I'm not gonna even show you this automatic calibration over and over, because I'm gonna use it for the first time here, and then I'll use manual calibration. Otherwise it will take a lot of time, but you can try both. Like first use that automatic calibration, get the parameter, and then use it into your model, and then change the parameter manually, and then check it. And again, you can even run your automatic calibration. Both way you can even do that. That will even give you more accurate results. But for the sake of time, I'm not gonna make the longer video, so we are done. So that's why I'm just running. So whatever we have, let's check the results. So let's see the objective function. The objective function we are getting here, see the simulated value is basically 3.37 and the observed value is 3.38. So it is pretty close, right? So difference is nearly 0. And we have this percentage 0.3. It's pretty good. And see the observation, we have 10,000 and we have almost 10,000, right? 9,952. And we have a little difference between the peak time. That's okay, because the shape is a little bit different. So in terms of this, it is looking like the volume is pretty accurate. But what about the shape? And we can see the optimized parameter. We can see initially the initial obstruction value, whatever value we had, it doesn't matter. It assumed as 1, and it is giving us the option that, okay, if you want to get the result that we just saw, we have to multiply that value by this one. And for curve number, we have to even increase it as like 1 point, is like 19%. And for this one, we have to increase it, and we have to change these values like that. We'll do that. Okay, no problem. So let's see the function, objective function. So initially it was just kind of changing, and then it became like stable, right? So let's see the plot outlet, okay, because we are calibrating the model at the outlet means here. So at first check the graph if it is scanned. Oh man, it's really good. See, it's really good, right? Yeah, so that's why I like automatic calibration. So I'm removing the extra plot we have. Okay, so that is the plot. We need to capture it. It's pretty good. See, but we need to even fix this. That's okay, but it is capturing, almost capturing, right? The volume it captured. And we can check the summary table, and oh man, it's really good. So 0.86 from 0.26 to 0.86. It's really good. And we can see the percent bias is like 0.27, right? And the peak, we know already, right? The observation, it has like 3.38 inch. However, from simulation, we are getting 3.37. It's really good. So that is the plot we have. Even you can use that. It's okay. But what we have here, we have some time shift here. We have to even capture this rising limb. Otherwise, we have a delay, right? This blue line is basically using more time to concentrate. That's why we have to reduce the time of concentration. So from this plot, we can see we need to shift this graph from here to there. So we don't need to lose any water, other than losing any water. So we're done with loss factor. So what we'll do next time, we'll even use calibration for the Clark unit hydrograph, the transform method, because we need to transform the depth of rainfall into this hydrograph flow rate. So transform method will do the job. But before that, what we have to do, because our model main simulation is not capturing this shape. This is our main model. We have this shape, but from optimization, we're getting this one. So we have to be able to get this, right? We have to be able to achieve this graph from our simulation. So how can I do that? So that is the thing I'm going to show you. We have the function, we have the values optimized parameters. So keep that in mind there, and go to your component and then model, go to parameter and the loss factor here. Okay, open that, optimized parameter. So what do we have to do? We have to change it. For the first one, initial obstruction, we have to multiply these values 1.2271. So this one will be multiplied by 1.2271. So select that 1.2271. Select that and click on fill, multiply by constant 1.2271. So it will be multiplied by this value to all of this. So now we are getting this one. Another one is that curve number. Okay, this one, curve number scale factor. So this curve number should be multiplied by 1.920. So select all this curve number at once and right click and fill, and again multiply by a constant. That will be 1.192. Okay, and then we have this. But see, it's not even, we know the limit of curve number should be within 100, so it is not realistic, right? So what do you have to do? Even though the optimization, it doesn't have that idea on that, so what it did, we have to change it. Okay, so I'm just canceling the, okay, I cancel that and I have to change it. Go back to your computation, the parameter we use, the second one, probably the curve number here. See, it's, even though it's 1, means initial is 1, the value we are using, and the maximum is 100. This is basically the factor, not the value. That's why it is going to give us that average number if you multiply that. So you have to even think about that. Okay, my maximum value of curve number is 100. I cannot go beyond that. So if you use that more than 100, the model won't run. So again, I'm going to open the parameters, loss factor. So instead of changing that, because I know from the optimization, right, that it is going to be more than whatever value we have, and it has to be increased. So this is my optimized parameter, and these are my curve numbers. So at first, again, I'm doing the same thing. I'm increasing this one. I'm multiplying this. This is okay because it has to be 0.2271. I'm multiplying that, so that's okay. But for curve number, instead of doing it like more than 100, I'm just putting it as 92. Okay, 92. So I can add it. So I can add 5, I can add 7. So I'm adding like 7. Okay, I'm putting it as not 9. Okay, so minus 2, so it is going to be like 92. Apply, and that's okay. So now if I even run it, now whatever value we added, we have to run our main model, the simulation. Okay, and we have to check it if we are getting the exact same shape of the hydrograph. See, now it's increased a little bit, but it is not as good as we just saw because we didn't change the routing parameter as well. And let's check. See, it is even 0.61. Previously it was 0.26, but it increased. Now what we have to do from the optimization, we need to change the routing parameter as well. We didn't change that. So again, I'm gonna open the parameter and then routing. We use the Muskingum method, and here we have to select this, and we can even add all this. Okay, so for river 4, the x value will be this instead of that. Okay, it has to be 6.1282. okay, and then the x value will be 0.39 instead of 42. 0.393. That's okay. So for river 3, the value will be reduced. Okay, 6.4479 and the value of x for reach 3, it is gonna be 0.278, 0.278, and for reach 2 the value 6.12. It's 6, so just 6.12, didn't change that much. And what will be the value of this parameter? Nearly 0, so we can even keep it 0.04. There is no, so whatever we are getting from the upstream, it is just quickly shifting the flood without just reducing the peak or shifting the peak. So for sub river number 1, the last one, we have 4.25, but it is going to give us 3.82, and then this value is also basically 0.8. okay, we can use like 0.1 as well, not a problem. So I'm closing this, and again I'm saving the model, I'm just running it. So it takes a lot of time and passions as well. So let's see what I have got from the simulation, and it increased a little bit, right? And let's check the summary. So it's 6.3 instead of 6.1, so it is increasing a bit by bit. So even we can't increase more because the graph we got from optimization, this is for more than 100 curve number, but that is not realistic, so that's why we're not taking that value. So whatever value we have other calibration parameters. So we are done with our loss method, we're done with our routing. So we have transform method, right? This one, Clark unit hydrograph. So whatever value we have here, this value looks pretty big. That's why we have a curve. That curve even giving us a hint, right? That okay, we have to shift the curve on the left. See, we need to shift it on the left side. So if your time of concentration is high, that means it is taking time to concentrate and then flow. So that's why the flow is starting at a delayed. The flow is being delayed. So it has to be fast. So we have to reduce the time of concentration. If you want to reduce the time of concentration, what we have to do. So for all of this, what I can do, I can even reduce this value by what will be the value I can reduce. We have this, so I can even multiply a factor. That's what I do. Instead of doing this, what I do, I just multiply, or I divide by this one or that one. So instead of doing that, I can 70%, or I can even reduce 50%, right? So I can multiply this value, let's see, by a constant like 0.75. okay, I'm multiplying this, so we are getting this, and apply, and let's see if we can get any increased or improved shape. And going to result and check, yeah, it is maybe shifting on the left side a little bit, but at the same time we have to even reduce the losses as well. So we'll do that, just capture the shape first and check. See, it's increased 0.776, so from 0.26 to this one, so it's working. And one thing we have even there, storage, right? So we are there, transform. So if you want to even capture the shape, you have to play with this transform method. So here, instead of doing this big value, because these sub-basin number 2 and 3, these are basically these sub-basins, you can see these are the most upstream, 1, 2 and 3. So we can play with all this thing. So for this one, I'm gonna reduce it to 200, and similarly, okay, let's run first with this one by one, because this is the manual calibration we're talking about. So close, and let's check. Yeah, it increased. See the difference reduce and it increase a little bit, and we can check. See 0.80, right? It increasing means it's improving. So we have other parameter as well. Let's transform method Clark. We can even change this, can reduce this, because if you want to increase the volume, you have to reduce the storage coefficient. Okay, so that will be okay, 100. Let's see, 100, and let's run it. So this is how we have to even fix that. Manual and automatic, we can't see the difference, maybe a little difference. We can check 82, and I can even transform method. Okay, I can reduce it to 90, and then I won't do that anymore because I don't see any change. Let's run it and check the graph if it improved or not. Yeah, it improved a little bit, and we can check that value, 82. Okay, so that's it. So whatever value we are changing, now we have to reduce the loss, right? We can see that, okay, still our model is underestimating the stream flow we have. We have to even reduce the loss so that we can even diminish the gap between these two. So we have only three things, like loss, transform, and then the routing. So let's play with the loss. We have to reduce the loss. We're going to reduce the losses, and then what we can do, okay, so instead of using 30, we can even 20, we can use 30. Okay, we can use 30. You can select, right click, fill, add constant. So we are going to add 10% to all and apply and see, because we're increasing the percentage imperviousness so that there will be less loss, right? So it will even increase the flow, and we can even run it. Save the model and run it. Okay, so let's see if we get anything. Okay, yeah, it improved. See, we reduced the gap. That is pretty good. So from the summary table, see, 88, it's really good, right? We already got 88 without capturing the shape. 0.88 NSE 0.88 means it's really good. So we have a very good shape. I can even show you that one as well after removing this element. Okay, so that's that. See, the shape is really good, right? Yeah, shape is really good. Only one thing we need to do. Okay, at first we need to reduce the gap, this gap. So the loss should be less. Then we can capture, we can even reduce this gap in between these two. That's okay. Yeah. So in terms of volumetric comparison, the model is performing pretty good. So what else we can do? You can go to parameter and go to this loss, SCS loss method. So initial abstraction, this shouldn't be this one. We can even reduce the initial abstraction, like from 0.61 to, okay, 0.6 or, okay. I can even reduce it from this one. So minus 0.05. How about that? Let's see. So 0.56, that's okay. We can even run with that one because initial abstraction is less. There will be less abstraction, so more runoff. We can increase the gap between these two. There will be lower loss. Maybe we can get more closer. Okay, yeah, it even close to that one. So you can see 89. That means it is increasing the performance. Okay, so we can play with that parameter. We can even play with this one first. We can even reduce that minus 0.0. Okay, then 0.02. Let's play with that, and then we'll even play with individual sub-basin. Okay, if it won't work, let's see. Close and check that. Yeah. Or what will happen if we individually reduce? Yeah, is there any increment? A little bit, but Okay, see your curve number, and here I can even reduce this value drastically to 0.3, or okay, not 3, 4, or 3.5 is okay. And for, because I'm doing this for upstream, and this value I can even do it as 0.35 as well. And subbasin 1, I can do the same thing for all these three, the upstream, 0.35, and I'm keeping this as it is, and let's run it if we can get any improved value, because the initial abstraction won't be same for all of this, right? That is even realistic and expected. And see, we can get the closure curve and check that. Yeah, it's 90, 0.90 is pretty good, because I want more. So what you have to do, you have to keep in mind that, okay, at the same time you have to capture the peak and you have to capture the volume as well. Okay, so we can even reduce that a little bit and go to parameter loss, and instead of reducing the 6, this is the middle one, even I can reduce. Okay, I can even reduce for this one that are even close to my outlet. Okay, like this one for the first time I did it, and then for 7, and we have 4, so we can change this parameter like 7 and 4. Okay, we can change the same like 3.5 and 4, do the same thing as 3.5. Yeah, this is the boring job you have to do, and let's run it. Okay, and then it's done. Check, maybe it's even closer, right? Closer than before. Okay, that's pretty good. And let's see. Yeah, we have 918 when it's increasing. It's really good. So one thing we can do is, still our model is underestimating, so we have to even reduce the loss, then we'll fix the transform. So from parameter loss, and we are just doing the same thing there. So instead of doing that, even we can use 0.30. Okay, there, 0.30, and let's see if we can get any improvement. Okay, yeah, it is kind of touching that, but we need more. Maybe it improved 918, that's okay, but I need to touch that line. That is my objective. Loss, SCS curve number, this time I'll reduce this one to 0.30, and then I'll do the rest of the thing for other subbasins as well. That doesn't matter. So here, run it, and let's check. Yeah, maybe it's been pretty close a little bit, but we can't even see that, but we can check it. 9.2, it's already 9.2, that means it is improving, right? So another thing we can do, loss method, SCS curve number, and then we can even reduce the values for 3, this one 6, right? What is the value of subbasin? Or it's subbasin number 6, so we can do this to subbasin number, this one 3. Oh, we have to even reduce this one 0.30, so that we can get any improvement there. Okay, so save the model. Definitely it will improve this time a little bit, I guess. Yeah, it's touching, I guess, right? It's close enough to touch that. And then we have even 923. That means if we even reduce the value for other as well, everything, 0.30, 0.30, and this one 9 is basically 0.30 as well. The 9 is the outlet that is draining directly. Okay, so let's see if we can, definitely will get some visible improvement there in the graph. Yeah, it's touching that, see, it's touching now. So, and you can see it's 9 to 8, and we can even okay, let's investigate the graph. We can even increase it a little bit, right? So I can even reduce the loss for this 2 to 0.25, and this 0.25, and for this upstream. Okay, I'm doing this for this 3 upstream sub basins. And now if I can do that, You close it and then see the graph, it's touching, pretty accurately touching. Okay, so that's good. And let's check that is 9.3. Even okay, I want more, okay, because it is responding the way I'm expecting. So reduce that to 0.25, reduce that to 0.25, and for 4 and 7 as well, 0.25. Okay, so let's see, save the model and run it. Hopefully it is gonna work this time. Okay, so it reduced the gap, it pretty accurately tossed the peak, and we can see any improvement there. So 932. And let's investigate further what we have to do. I think we are done with this one. Other than capturing this peak, we can even match these two, right? We can reduce this gap. So we can use our time of concentration to do that. So go to transform, Clark unit hydrograph, and reduce this time of concentration. We can play with that one as well, right? We can use 50 and we can check that, okay, if it works, and run it. See how many times I'm running the model. So it's really hectic job. Maybe it shifted a little bit, that's why it is crossing that line. And if I even reduce the time of concentration for this one, okay, use 40, and then saving it, running it again. Let's see. Okay, yeah, it shifted a little bit, I guess. That's what I can see. And if it improved 9.3, I don't know if it is going to improve, but we have to capture the shape now. We are working on the shape. And let's check if we can improve it more. Oh, not this one, because we are working on the transform method. Okay, so we can even use this one instead of 61. Okay, 55. Okay, 56. Okay, and then run the model and check it. Yeah, maybe it is just getting closer and closer, right? Okay, but at the same time, see, it is even increasing the peak. And let's check this one as well. It is 9.3, reducing the performance. Okay, that's okay. We can even reduce the loss. We can increase the loss. We can capture that peak, not a problem. So instead of doing that, I can even change everything. Okay, at first, okay, this time instead of changing one by one, I can change all of this. Okay, so instead of this, I can even use as 50, and then I can even use that 26 to 24, because these are smaller ones. So this is 16. Then I can use, okay, 14.5, and for 8 I can use even 30. This is a little bit bigger, and instead of 26 I can even use 20. That's okay. Instead of 20, okay, this is, I can 9. Okay, for 9 I can keep it as it is because I didn't change that much. 9 is at the end, right at the end of the watershed here, that is directly draining into the model. So let's run it. If we can see any changes, then we can change the value for 9 as well. Yeah, so see, it's getting closer, really closer and closer. So what is the value? See, 939, it's almost 94. It's really good, fantastic model. We can see the calibration is really good. Even if you want to capture this one pretty accurately, we can even do that, or we can even keep it as it is. See, I'm just cleaning it. Let's see, if I remove this curve, I can remove this one as well, and I can see the changes here. See, it's looking really nice, right? Yeah, it's really nice, and it is possible to capture, but yeah, it is also possible to capture, then it will be improving. But I think it's a really good calibration curve. The calibration curve is really good. Even it's really 939, and see the percentage bias is like less than 5%, right? and the peak we captured like 3.23, and the volume, these are the volume, and the observation is like 3.38, so it's pretty close. So I think it's okay to validate the model. The calibration is okay, even we can capture that one as well if you try, that doesn't matter. So that's that. So this is how we can even calibrate using automatic calibration, the optimization trial you have. And if you already have the model, then you can calibrate. But in this tutorial, I didn't show how to set up the model, but I have different videos. You can check that, how to set up the model from DEM data. So after that, you can even calibrate the model, but it is even customary to calibrate the model not for one single location. If you have like a larger watershed, then you can calibrate the model at multiple locations. But for doing that, we have to have the observation data. But for this watershed, I don't have observation data here or here. I have only one outlet there. So that's why I'm just selecting this point as my calibration point. And I think the calibration looks pretty good. It is almost 0.93. So now within this tutorial, if you have any query on that, you can mention that in the comment. I'll be happy to answer that question as well. So thank you very much for watching these videos, and thank you very much for supporting my YouTube channel. Bye.